Hi, this is Alex from devstories.eu. Shapely, episode 7 of 8. Try rendering a 1 million point coastline on a web map and you will quickly crash the user's browser. You need a way to reduce that data footprint to 1% of its original size while making it look completely identical. This requires advanced constructive operations. The core tool for this data cleanup is the simplify function. Listeners sometimes think simplifying a shape just means skipping every second or third point in an array. Doing that destroys the geometry. It creates self-intersecting lines, collapses small islands, and ruins the topological structure. Shapely's simplify function evaluates the actual geometry. You pass it your complex coastline and a tolerance value. The function removes vertices that do not deviate from the core shape by more than that tolerance. Crucially, Shapely gives you a flag to preserve topology. When enabled, the algorithm actively checks if removing a point will cause a polygon to cross over itself or split into invalid pieces. It guarantees your highly compressed coastline remains mathematically valid. Once you simplify a heavy base layer, you often need other layers to align with it perfectly. Say you have land parcels or property lines that end exactly at the water. Because you just simplified the coastline, its edges have shifted slightly. This creates microscopic overlaps or empty spaces, known as slivers. You fix this using the snap function. You provide your property line geometry, your coastline geometry, and a strict tolerance distance. Snap looks at the vertices of the first shape. If a vertex sits within the tolerance distance of a vertex or segment on the second shape, it gets pulled directly onto it. Points outside the tolerance stay exactly where they are. This creates a watertight, flush fit between adjacent geometries without distorting the rest of the shape. That covers cleaning up existing shapes. The other side of constructive operations is dividing empty space by points. If you take the vertices of a geometry, you can pass them into the Delaunay triangles function. This connects those points to form a continuous mesh of non-overlapping triangles. The logic specifically draws these triangles to maximize the smallest internal angles. This prevents long needle-like triangles, creating a balanced mesh highly useful for rendering terrain. If you only want the outline of these connections rather than filled shapes, you can set a flag to return just the line edges. Closely related is the Voronoi polygons function. While Delaunay connects points, Voronoi draws boundaries between them. You provide a geometry and Shapely uses its vertices to divide the surrounding area into completely distinct polygonal regions. Any location inside a specific Voronoi polygon is closer to its central generating point than to any other point in the entire set. If you are analyzing a scatter of delivery hubs, Voronoi polygons instantly map the exact coverage zone for each hub based on pure proximity. Just like Delaunay, you can instruct the function to return only the boundary edges if you do not need solid polygons. Here's the key insight. Real-world spatial data is dense, disconnected, and rarely aligns perfectly. Constructive operations like simplify, snap, and Voronoi give you the tools to enforce mathematical order, making the data light enough to render and precise enough to analyze. Thanks for spending a few minutes with me. Until next time, take it easy.